In this video, we're going to look at using distance time graphs to find the speed of an object, except this time our graphs include curves. In the previous video, we saw how we could find the velocity of an object on a distance time graph. We could do that simply by finding the gradient of each section of the graph. Before you continue with this video, make sure you are happy with the difference between a velocity and a speed. If you're not sure about that, go back to the previous video. Let's take a look at this example then. A marble is dropped from a tall building. The graph shows the distance travelled by the marble as it falls. So we drop the marble when the timer is at 0. After 2 seconds, it looks like it's fallen about 20 meters. After 3 seconds, it's fallen a bit more than 40 meters. After 4 seconds, it has fallen about 80 meters, and so on. Now, these questions are asking us not how far it has fallen at given moments in time, but how fast it is travelling. And this is a distance time graph. It is not a velocity time graph. So we can't just read off how fast it is travelling at any given moment in time. What we have to do is try to find the gradient of this curve at those given moments in time to find the velocity and therefore the speed at those moments in time. The problem is finding the gradient of a curve is not as easy as finding the gradient of a straight line. There's going to be an extra step involved. Before we do that, let's have a look at this third part. Does the graph show the marble accelerating, decelerating, or travelling at a constant speed? Accelerating means getting faster, decelerating means getting slower. Travelling at a constant speed obviously means just travelling at the same speed throughout. Now, keep this big idea in mind. For a distance time graph, the gradient gives us the velocity. And of course, from the velocity, we can easily write down the speed. So how fast is this marble travelling to start with? Well, if you look here, the gradient is actually really shallow. It might even be perfectly flat just there. So it's got a very low speed or maybe even 0 speed. As we go further along, let's say to here, you'll see that it is a bit steeper. So the gradient has got higher, which means it's going faster. The marble is going faster. If we go a bit further along, you'll see that this is steeper still. So the curve's gradient around here is getting even higher. And you'll see that the curve is even steeper here, so the gradient is increasing, which means the marble is getting faster and faster throughout. So that means the marble is accelerating. It might be helpful here if I give you an illustration of deceleration on the same axes. The green curve here gives you an example of something decelerating. Now, this confuses a lot of students. Some students were thinking, yeah, this is acceleration because the curve is going up. But that's not the reason why this was acceleration. Because here we have a curve that looks like it's going up. But I'm telling you this is deceleration. Like I said, the important thing on a distance time graph is that speed is found by calculating the gradient. So we're not interested in whether these curves go upwards. What we're interested in is the gradients to decide whether something is accelerating or not. And in this red case, we saw it was accelerating because we had a low gradient or a low speed, and we ended up with a high gradient or a high speed. Now that's the opposite in the case of this green one. At first, you can see this is really steep. So that means we've got a high gradient or a high speed. But as we go further along this curve, you'll see that it's getting less and less steep. If you imagine walking up this thing, it would get easier and easier. So that's because the gradient here is getting lower, which means the speed is getting lower. So this represents a decelerating object. Now, let's go back to the previous two questions. First of all, we want to work out the speed of the marble at 2 seconds. I'm going to do this by drawing a straight line that just touches the curve here, that has the same gradient that the curve appears to have just there. This line is a tangent to the curve at this particular point. That means if you zoom in really close to that point, you'll see that the line just touches the curve there without crossing over it. Now, when you try to draw a tangent to a curve, I recommend you use a really sharp pencil and of course a ruler. So instead of trying to find the gradient of the curve at that particular point, I'm going to find the gradient of the tangent, and the idea is that the tangent has the same gradient as the curve did at that particular point. Now remember, the gradient is the change in this direction divided by the change in this direction, and what I can do is make my life easier by choosing a sensible value for the change in this direction. So we've got an easy number to divide by, and I'm actually going to pick these points here because that gives me a change in this direction of 2. That's 2 seconds, the difference between 1 and 3. And the change in this direction is 40. That's from 0 up to 40. So the gradient is 40 divided by 2. And that is 20. And the units are meters per second. Now, because I worked out a gradient, what I really worked out here is the velocity. However, because it's a positive velocity, in this case we know the speed is the same thing. So how fast was it travelling? 20 meters per second. Let's have a look at this one then. How fast is the marble travelling after 4 seconds? Well, this time I need to draw a tangent to the curve at this point here. Now I'm just going to clear away the previous workings to give myself some space. And I'm going to draw a straight line that just touches the curve at that one point and has the same sort of gradient as it does right there. Now I've drawn this tangent to the curve at that particular point. Pause the video and see if you can find the gradient of this tangent, and therefore the gradient of the curve at this particular point. You should have found that the gradient of the tangent is 40, so that means the velocity is 40 meters per second, which in this case means the speed is 40 meters per second. Of course, there are lots of ways you could calculate the gradient of this tangent, but I like to make my life easy. So for example, I would choose some friendly looking points like this one and this one, because I can see that my change in this direction is 2, and that's a nice easy number to divide by. That's going from 3 to 5. That gives me a change of 2. Going this way, I can see that I've got a change of 40 up to 120, which is 80. So 80 divided by 2 would give me that 40 meters per second. Of course, I didn't have to pick these 2 exact points on the tangent. I could have picked any 2 points on the tangent and used those to help me calculate the gradient. But I still should have got 40 as my gradient, 40 meters per second. So, to summarize this video, if you've got a distance time graph and that graph is curved like this, and you want to find the speed at a particular moment in time, what you can do is draw a tangent to the graph at that particular point. Then find the gradient of that tangent to give you the velocity. And once you've got the velocity, you can simply write down the speed. If it's positive, the speed and the velocity will be the same thing. If the velocity is negative, simply take the positive of that as your speed.